How's it unique from Gen Chem 1, I guess? Gen Chem 2 is going to be a little bit more on the math side of things. For 70% of you, you guys just had that moment, right? It's going to be a little bit more focused on the formulas and that kind of thing, which lends itself to be, how do we want to say this? Kind of to shake out in two ways, right? If you feel comfortable and confident in your math skills, and then maybe it's going to be a little bit easier for you guys. But if you're not, like I wasn't when I went to Gen Chem 2, right? As for those of you guys who've had me before for a class, I'm not making it up to relate or whatever you want to say with that. It's like math wasn't my strongest skill. It still isn't, right? And I made it this far at least, right? But it's not because I just sat passively by and said, well, I don't understand this, and I just hope it never comes up again. Okay, it's going to come up again, and the math isn't going to get easier by you guys ignoring it or not wanting to do it or not needing to do it or whatever it might be. And so I'll go ahead and give you the trick on how to get through Gen Chem 2, right? Now it's a trick that you guys already know, because you've been doing this your entire academic career so far, right? So I'm going to give you the trick that you already know. I'm going to ask you guys to see the forest and the trees, right? What do you think's the big secret to getting through Gen Chem 2? I'll give you a hint. Some of you guys might have spent a couple $100 on it. Huh? Yeah, your textbook, right? Look, here's the thing, right? I'm going to present these equations to you guys, and they're going to have a lot of variables in there, right? And you guys are going to say, that sucks, it looks like alphabet soup, right? And it does. But if I give you guys an equation, right, with 5 variables in it, what do I have to give you information about? 4 of those, right? And you guys can figure out the answer. Or I can give you an equation with 13 variables in there, right? And then what do I have to do? Hide in my office because you guys are going to get pissed, right? No, right? But I have to give you information about the stuff that's in there for you guys to be able to solve it, right? That's the point. And so really the challenge in Gen Chem 2 comes from just interpreting what in the world is information that you're given, right? And so it becomes a little bit more of a mix of reading comprehension along with math, which again kind of inflates the challenge there, so to speak, right? But the good news is that I'm not all that creative, okay? And what I mean with that is when I go to write an exam or a quiz and this kind of stuff for you guys, I'm not going to come up with my own problems. You know why? Because the book already did my work for me. Isn't that amazing? It's easy to be a professor. I got to work 2 hours today. I got to teach this class, and then I got another one later on. 2 whole hours of work all today, right? And that's all I do. What I mean with that is when I'm going to write an exam for you guys or a quiz, I'm going to go look for the book at the problems that are in there. And typically, if you guys were with me for a previous semester, right, when I write you guys a quiz, I'm going to look at the stuff that's in the chapter, the worked out problems. So you guys have a chance to be able to work through exactly the stuff that's in there and see if you get the same answer and understand that and go through it, right? And then when it comes to the exams, I'll probably look in the back of the chapter there, right? For the stuff that's very similar to what you see in the chapter itself, but maybe not necessarily have the answer right in front of you, right? So it'd be a good idea for you guys to set a regular schedule, a habit, whatever you need to do, right? Make sure that you guys are following along appropriately with that. Because the stuff will get kind of thick and heavy pretty quick, okay? Like the equations look kind of scary, the wording's kind of scary, the book kind of makes it intentionally scarier and just kind of giving you all this information. But all the stuff tends to be solved the same way, right? So all I'm saying with that is spend a little bit of time each day, right? Some of you guys it's gonna take a lot longer than others. Okay? Again, it just depends on how comfortable you are with your own math skills, is what it is. All right, good, yes. So I think there's my little spiel about Gen Chem 2, right? And you guys are all fired up, I can tell. All ready to go. So, we're gonna have some exams. We'll do them during the lab weeks there, kind of the same thing that I think all of you guys had last semester, right? I know some of you guys were with Dr. Tom, and that was the wrong choice. And some of you guys were with me for the last semester, that was the obvious correct choice, right? I'm being recorded, so I hope he sees this, all right? Anyway, but the point being, no matter who you have, right, all joking aside, right, we're going to be kind of handling exams the same way. You guys will be in a classroom. Hopefully we can find a classroom for you guys, and then you guys will be taking the exams during the lab times there, right? So we'll get that kind of worked out as we get a little bit closer to the first exam, but just so you guys know that, right? In terms of quizzes, I'm going to try and stick with about a quiz a week for you guys. We will do those online using the whole lockdown browser thing and that kind of stuff, which I think everybody's got that set up at least from a different class. Yes? No? Maybe? Somewhat? Some of you guys, yes. Some of you guys, no. Yeah, what's up?
I got a new laptop, so
yeah.
I gotta redo it.
Okay, that's fair. I'm not gonna I'm not gonna blast it out today or something, right? So I think that it shouldn't be too hard to do. But that's what we'll do in terms of quizzes, because I get the feeling that people will be still kind of in and out all semester long, given the circumstances, right? So we'll see how we can avoid any makeup exams and quizzes and that kind of stuff. But we'll adapt as we can, right? I think we've all been through one semester with this, so you guys kind of know the rigmarole of how it is. But just send me an email if you guys are going to be out. I probably won't respond if you say, hey, Dr. H, I'm not going to be there. It's not that I don't care, it's just okay, what do you want me to say? I got your emails, I promise, right? So just let me know if you're out, and then if you're going to miss something, let me know and we can work out, a makeup time or something like that with them, right? Does that make sense? All I'm really saying is communicate with me, right? And if you have a question about anything, or if you're not going to be here, whatever it might be, just send me an email. I promise I'll respond to you, right, at some point. I'm a little bit, my joking aside, I don't just work 2 hours a day, right? So I'm a little bit busy and behind on some of my emails and that kind of stuff, but I will get back to you as soon as I can, I promise you that. In terms of the labs, I'm not teaching any of the labs. That's, again, Dr. Tong and Dr. Fries are doing that. They should have their syllabus for you guys. So make sure that you guys kind of look at that. There should be a separate course for you guys on Canvas already, yes? Yes. Do you guys have a lab this week already? You do? No? Yes, no, maybe? I don't know, I'm asking you guys. Yeah. Okay, well, some of you guys may have a lab, we don't know, it'll be a surprise, but figure it out, right? Take a look at the syllabus, I know the schedule's in there for you guys for that too, right? So remember, the same thing with the lab goes as what it was last semester there. Make sure you guys come prepped, with goggles and appropriate attire and all that kind of stuff too, right? Yes? Anybody got new goggles for Christmas? No, what did you guys get? Useful things? All right. Anyway. All right, so I think that's kind of, let's see, we talked about quizzes and exams and how to get a guaranteed A in Gen Chem 2. What else do we need to talk about? I'm going to be recording the lectures. I'm going to be posting them to the YouTube channel there. I'm going to try and, I know I said you guys had an announcement about this too, but I'm going to try and figure out how to get Teams concurrent with a recording and all this kind of stuff, but technology is missing. So we'll try and figure something clever out. But if you guys are gone, there's always going to be a recording. It's always going to be online. And the good news about that is that you can watch me at double speed, right? So a 1 hour class just flies on by, right? So, but anyway. So if you do miss something, you're not going to be missing a lecture is kind of what it is. And hopefully we'll get the whole team things kind of settled too. Okay. Let's see, what other managerial things that I have to chat with you guys about. I think that's it. Do you guys have any immediate burning questions? Yeah, I'll get it. That's where I'm coming. All right. So, since you guys know everything about everything, which is what you said, you guys didn't have any questions, I'm going to go ahead and make a prediction. Now, what you guys didn't realize is that when you do become a professor, you get certain superpowers, right? One of these things is I can predict the future, right? Now, it's nothing useful, but I'm going to predict, right, that a certain percentage of you guys are going to start to struggle in this class at some point, right? And you look at me and you say, that guy's scary because he has a red tie. So I'm not going to go to his office hours, right? Let's see, and then you're like, well, I don't know what to do then, right? I don't know where to go, I'm not quite sure where to get help. Well, you're on your own is all I'm saying, right? No one's there to help you, and sorry, right? No right? Of course not. Look, there's plenty of help for you guys. I'm always in my office, okay? I've got office hours, I can't even remember what's on the outside of my door, okay? But I'll be there during that time, I'll figure it out, right? I think it's like in the afternoons on Monday and Wednesday or something like that, okay? But I'm usually in my office a lot outside of just, you know, the office hours that are there, right? So you're always welcome to come by and knock. If I'm there and you guys come by and you say, hey, Dr. H, do you have a couple minutes? I'll say two things. Yeah, or no, come back later, right? That's it. I'm not going to get mad at you. I'm not going to get upset at you. My job is here to help you guys out, right? And the only way I can do that is if I'm in my office and now you guys know where I am. I'm on the second floor, right? And come by, knock, hey, do you have a couple minutes? Yes or no. I'll answer yes or no, and we'll figure something out, right? So what I'm saying is if you got a question, just come by and see me, right? If I'm not in my office, I'll be back soon or whatever it might be. I am human, so I do eat, right? So, and I don't really have one of those out for lunch signs, but I'll be around and I'll be back, right? Otherwise, send me an email and say, hey, Dr. H, can we set up an appointment? And if you send me an email like that, just tell me what time do you guys have available. Because I get a lot of emails that say, hey, Dr. H, are you available? And I'll immediately email back, what time do you guys have, right? And then you'll email me that information anyway. So we'll simplify and just say, just tell me what time do you guys have. Do you have time to meet Tuesday at 3 o'clock, right? And I'll say yes or no. Got it? So that's fine. I'll get back to you guys. Okay. Now, if you don't want to come see me, right? We also have Laura, who's in the tutoring center over there. Laura, do you want to come and give a quick this and that?
Yeah, do you want me to watch it?
Of course I do. No, they don't want to turn around and just want to stare at you in the corner.
I do like the morning.
Okay, hi everyone, I'm Laura. If you came to me last semester, you already know me, but I'm the tutor for all the chemistry classes. So if you have friends in other chemistry classes, you can come with them to see me for tutoring. So tutoring for me this semester is going to be a little bit different, just because I have a more crazy schedule. So I won't be having regularly scheduled tutoring hours every week. That way I'm not just sitting in the tutoring room being sad because no one is coming to see me. Instead, I'm just going to be on my computer all the time, and you can message me or email me and we can set a time up. That way we're both getting the most out of our time together and we're not just sitting around waiting for the other to be available. Also that way we can have longer periods of time if you want to set up a one-on-one, if you want you and your study group to come in. There's just more flexibility that way. So you can email me. My Aave email is just like laura.osborne, blah, 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 blah. I'm also on the Tutoring Center Teams page, which you should all be on from last semester. If you're not on it, that's okay. You can just Google like Tutoring Ave Maria and get in there. But you can just message me on Teams. That's probably like the fastest way to get to me. And then we can just set up a time. So because I won't be having those regularly scheduled hours, it'll just be whenever you guys want. Another thing I'm going to be doing is I'm going to start hosting review sessions before y'all's exams. So I'm going to get the syllabus from Dr. H, and every time y'all have an exam, or maybe a bunch of you have a quiz you're really worried about, we will just set up a time either in this classroom or in the library or something, and we'll just come and we'll talk about whatever, we'll work through whatever homework problems. But that way we can all be together and it can be right before your exam. Because sometimes if I say only have tutoring hours on Wednesday and your exam isn't until the next Monday, you don't come see me and then you just have 5 days of study by yourself. But this way we can do it like maybe the night before, maybe 2 nights before, so that we can really drill in whatever y'all want done before your exam. So I'll be sending out messages probably in y'all's like Canvas page or something about like review sessions and that kind of thing. We'll probably try to do evenings, I think, just because that works better for people, but we'll cross that bridge when we get to it. So reach out to me if you want help. Besides that, I'll be around for review sessions so you won't forget I exist. And that's basically it.
They should be able to contact you through Canvas also, right?
Yeah, if you go into your, I'll be like in your Canvas page. So if you get into Canvas, you can find my name and click on it and message me.
I'm sure you'll post this kind of information there
Yeah.
when you get a minute too. So
Yeah,
so
I'll
by
probably,
email, by Canvas, by Teams.
all that kind of stuff. If you see me, you can also like nail me down, that too. And I won't remember who you are, but.
And they'll recognize the top third of your face, right? So.
Exactly. But yeah, so I'll send this also out like in a Canvas thing, so you can get all that information and all that.
And what is it, this semester, it's only $35 an hour? Is that what it is?
50.
Oh, it went up, oh my goodness, jeez.
No, it's free, you're fine.
Absolutely free, right?
So
You
this
guys
is
are already,
me to help you.
that's right.
so that you don't have to.
You guys are already paying for these services, right, is what it is. So, you don't have to do it, but it's you're right, it's your choice, and it's available, and it's there, and, you didn't take Gen Chem with me, I forget now, right?
No, I took it a very, very long time ago.
Yeah, right. But Laura's been, is a senior now, right, and graduating in biochem, so she absolutely knows what she's doing with
Taking
it.
all the chemistry classes here.
There you go. Where else would you take? Right? No other choices. Right, so Laura absolutely knows what she's doing, and she's also, she was in my organic class, and so when you guys get through organic, well, never mind, you're graduating, right, so.
Yeah.
Okay, well, you can contact her at med school or wherever she's ending up, right, so.
But it's also like, I know how heat tests or all that kind of stuff, so if this is your first time in the class,
Yep.
I have all the tips and tricks.
That's right, so she'll prep you guys for the physical fitness portion of the exams, right?
Yeah.
10 push-ups while doing that's easy, all right. So, anyways, I think that's all the stuff that I really needed to share with you guys. Again, if you have any questions, just swing by or contact me or Laura. Joe is not tutoring.
I do not know if there are any other chemistry classes here. I'm not sure.
Chase the rest of them away. Makes sense. All right, very, very rigorous.
Means you get to talk to me that much more.
All right, cool. All right, so if you guys have any questions, then feel free to reach out to me, and we'll get right to it then. So, all right, so where we're gonna start, I guess, is a little bit of a review from Gen Chem 1. Now, the reason why we kind of start here, and if I had my ways, we'd kind of put this at the end of the semester because it's a natural progression into organic chemistry, but unfortunately, I don't make all the decisions here, or fortunately, I don't make all the decisions. So what we want to talk about is just why things are solid, liquids, and gases, and what influence does that have, or what do we need to pay attention to, or why do we care, right, that kind of thing. So I'm kind of drawing together parts of chapters 11 and 12 into here. I know we already talked some about chapter 11, but we're just going to kind of review that a little bit because it's honestly one of the most important parts of all of chemistry. And then we'll kind of tie into some new ideas here that will relate to the next chapter we'll get into, which is kind of the solubility and solutions and that kind of stuff, okay? So we're going to talk about the intermolecular forces as kind of the main idea here. Now, we're going to talk about something that's new, right? Did you know that there are different states of matter? Wow, right? We have our solids, we have our liquids, and our gases. Now, we talked a lot about gases last semester, right? We had that entire chapter about gas laws and the ideal gas law and the relationships with pressure and volume and temperature and moles and all that kind of stuff, which you guys all remember. No, nobody remembers. I see nothing but just shocked stares. Yes, gas laws a little bit, somewhat, kind of. What's the big gas law that's, equation that you guys are probably expected to memorize? Yeah, do you remember what it is? There you go, right? PV equals nRT, right? So remember that was an entire chapter that kind of dealt with all that stuff there, right? So fortunately, we don't have to go back through that stuff because you guys already passed that part of the class, right? Now, we're going to be coming back to some gas law type stuff a little bit later when we talk about equilibrium, right? But, I guess the point I'm trying to make is we understand what's going on with gases and what it is. Now, we also talked a little bit about liquids and solutions last semester, right? We talked about solubility rules. You guys remember those? A little bit, maybe, kind of. You guys remember the precipitation reactions? Where you guys mix two ionic solids and something precipitates out, right? And you guys have to predict the net ionic equation and the complete ionic equations, yes? Did we ever talk about why certain things are soluble, though? Or did we ever talk about why certain things are insoluble? No, we just kind of looked at that table of solubility rules and went through that, right? So one thing we'll start to kind of draw out from this chapter is a little bit about how do you predict whether things are going to be soluble or not. Now I think you guys had a lab last semester where you guys were trying to dissolve different salts into waters and different solvents. Was that you guys? Right? So you guys started to talk a little bit about this there, right? And so we'll kind of just put the pin back into it here just so it sticks, right? But anyway, just to kind of summarize here, you know, you guys know about solids, liquids, and gases. Unfortunately, we don't really talk too much about crystalline solids in this class. I just don't, I'll be honest, like they want me to talk about it with you guys. And then they want us to sit there and look at unit cells and, okay, here's a face-centered cubic and blah, 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 blah. Just, it doesn't add anything to you guys, right? And so my view on things for you guys who are new is I'm not gonna introduce anything to you guys that either, how do I wanna put this? Everything I try and introduce to you guys will be something that we build upon later on. I'm not saying it's necessarily immediately going to be within that chapter, right? And if you go back to what I was just talking about earlier, I said this is one of the most important chapters, not just because of what we're going to do in Gen Chem, but for those of you guys who are going on to organic. How many of you guys are going on to organic chemistry? All right, so I'm going to see you guys again, probably. All right? But for those of you guys who are going on to organic, these intermolecular forces are key essential ideas and concepts. And when I get into the first semester of organic chemistry with you guys, I'm going to ask you guys a question. I'm going to ask you guys, what do you guys remember from Gen Chem? And you know what answer you're going to give me? Yep, that answer right there, right? The dead silence. I don't know, Dr. H, that was like 2 months ago. I don't remember that, right? But here's the thing with chemistry, and again, maybe I don't want this to be story time with Dr. H, but I wasn't always a chemist. Right? I started out in engineering, and then I ended up taking organic chemistry as part of that sequence, and then I switched at that point, is what it is. And so when I went through Gen Chem, I hated it. I was like, what's the point, right? Okay, so you memorize this, all right, periodic table, blah, 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 yada, yada, all these kind of things. The thing with chemistry is it's not really until you get to biochem, right? Where you're like, crap, I should have remembered. What do you need to remember for biochem?
All of it?
Oh, there you go, okay. So you need to remember everything, right? Why do we call this general chemistry? Is it because it's just general knowledge and it's good to remember for the bar trivia so you win a tab? No, right? It's because this is the foundation that everything else kind of builds up on, right? The idea of how solids, liquids, and gases behave affects, you know, biochemistry and organic, and we don't do inorganic chemistry here or physical chemistry, but all these things we're laying the foundation for this stuff, right? This is so, what I've realized in my career at least is that Gen Chem is the thing that I keep referring back to over and over and over again when I, start to teach these more advanced classes, right? So what I'm saying is that when I give you guys this kind of, hey, we'll do this in organic chemistry, or hey, we'll come back to this later, this is something to pay attention to for you guys who are moving on in chemistry, right? Because if you do a good job of remembering this now, and you start to understand the ideas behind it now, then it's going to make your life in OChem that much easier, right? It's still gonna be difficult. I'm not saying it's going to be that much easier. You don't have to relearn Gen Chem, is what it is, right? So, but solids, liquids, and gases and the intermolecular forces is kind of what the first main topic is here, right? Now we talked about kinetic molecular theory and all that kind of stuff, and we talked about temperature quite a bit in the first semester there, and we'll see that come back a little bit here. But the thing to really pay attention to are those intermolecular forces. Now I've got a little bit of an argument with some of these textbooks. They say, I think some textbooks say there's 3, some say there's 5, I think your textbooks say there's 4, whatever, right? I'm not too interested in how many intermolecular forces there are, aside from you guys understanding these 3 right here. Because if you guys understand these 3 right here, then it doesn't matter. Because in reality, there's probably close to 20 or 30 intermolecular forces. We just don't talk to you guys about them. Do you know why? Because I can't lock the doors from the outside. You guys would run screaming if we have to talk about all these 20 different intermolecular forces, okay? But here's the thing, right? Do you think I have memorized all of those 30 intermolecular forces? No, you guys think I'm dumb. Okay, fine, all right. Here's the thing, how do these intermolecular forces work? That's the question to ask. What's going on behind the scenes with these things, okay? Do I need to sit there and memorize the 3 intermolecular forces? Maybe, right? If that's what you want to do, it's your choice. I'm not going to tell you how to learn something, right? You guys know better than that about yourself, right? How you learn things. But what I want you guys to think about a little bit is how do they work, right? Now, they're on the screen there, right? There's kind of an eye exam, maybe if you're in the back of the classroom, right? But my lecture slides are online for you guys too, so you can print them out and bring them in if you'd like, right? So what are the three intermolecular forces? What do you guys remember with that? You're closest to the board. What do you read there? What's number one? Dispersion forces, right? So, what do we remember from dispersion forces? A couple of very important things. What do you guys remember? Yeah.
Weakest of the three.
Huh?
Weakest of the three.
Ah, what do you mean by the weakest?
So the forces that hold the molecules together are the least strongest.
The least strongest forces between what though?
Two molecules.
Aha, between a set of molecules, right?
Yes.
So remember, when we're talking about intermolecular forces, right, we're talking about how one molecule talks to the other, right? That's why some of you guys sat next to each other and some of you guys didn't, right? Why do you guys sit next to each other? Well, there's only so much space, Dr. Reeves. No, I got that, right? But you also, right, you come in here and you sit next to your friends. Why? Is it easier for you to communicate with somebody you know? One of you guys is answering yes, the rest of you guys are like, no, I'm good. I'm very social, I just talk to everybody. Right? Do you guys get the point I'm saying here? You sit next to your friends, you talk to the people who have similar interests and all this kind of stuff. How do you think molecules behave? The exact same way, right? They're going to talk to something, it's going to be easier for them to talk to something that has similar properties, similar behaviors, similar atoms, all these kind of things, right? So it's the exact same way here, right? So dispersion forces, like Andy was talking about there, it's he mentioned that they're the weakest. Why? What makes a dispersion force?
Probability.
Aha, probability of what?
It's very short-lived, right?
Yeah, you're hitting the bullet points for it, but of what? Probability of what? You know, the temporary nature of what?
The electrons.
The electrons, right? So here's a good answer. I'm gonna give you guys, I don't know, it's the first day. Should I give them all the secrets to success already? You guys might not come back. I'm like, no, you told me it's not just kidding, right? There's always two very good answers in all of chemistry, okay? For everything, all the way up through biochem, okay? The two smart answers are sterics and electronics, okay? Seriously, this worked all the way through grad school, even when I was doing my doctoral defense, right? That's how I started my answers. Oh, professor, oh yeah, very smart. Right? Sterics and electronics. Sterics is basically an argument arising from where atoms are, how they are arranged. If you remember back in Gen Chem, we talked about geometries. Right? Linear and trigonal planar and tetrahedral and octahedral and bipyramidal and T-shaped and blah, 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 blah. Yes? All those that you guys all have here still? No, none of you guys. Man, who did you guys have for Gen Chem? Man, that guy must have stunk. Oh, it was me, crap, right? Right? But that's the sterics, okay? How the atoms are arranged, how the molecules are physically arranged, okay? Electronics deals with where the electrons are, okay? If we know where the electrons are, we know how to do chemistry. Why? Well, what does chemistry? The electrons. Okay? All of the chemistry that you guys are going to learn from now until the end of time, well, unless you guys become nuclear engineers, right? So, with the exception of nuclear engineers, the chemistry that you guys are going to learn are where the electrons start and where they end up. That's really it, okay? And that's why I became a chemist, because I can remember two things, sterics and electronics, okay? So if you guys can remember that, then, sorry, you got to become a chemist, right? You've got no other choice, right? Oh wait, we don't have a chemistry major. Do you guys still have a chemistry minor here now? I forget. Is there still a chemistry minor? Okay, so you can become a partial chemist, which is, yeah, not too bad, right? But anyway, so those are the two smart things there, right? So when I ask you guys a question on an exam maybe, or a quiz, and I say, explain this idea to me, and you're like, I don't have a clue on how to answer that. go back and think about those two places to begin with. Because when I ask you a question, why do dispersion forces happen, or where do they originate from? And you're like, I don't know. Your first thought should be, well, does it have to relate with sterics? Maybe, right? Does it have to relate with electronics? Maybe, right? And then you start to branch your way out from there, right?
Can you explain those two again, sterics and electronics?
The kind of the definitions?
Just what are they?
Well, okay, so the answer, I can't answer that for you, because we have to apply them a little bit differently in each case.
Okay.
Right, so what I was about to say, and maybe this will help answer your question, is whenever you guys do answer sterics or electronics, my immediate follow-up is going to be how, or why, or what do they do, right? Because in different cases, those sterics and electronics are going to impart different properties, okay? And we'll talk about that in just a little bit here, okay? But I'm giving you guys a starting point so that you're not just, out in the middle of the ocean just kind of treading water. Fix your eyes on the distance and start moving towards that target, right? Okay, I'm going to explain sterics, and then you start explaining it down that pathway there, okay? But anyway, so the question was, well, what are dispersion forces? And Andy gave the answer of they are temporary and, what was the other? Something about probability, right? So temporary and probability. Of what? Of the electrons. Now, where do electrons live? Shells. So they live in by the ocean, right? And the conch shells, right? Native to South Florida. What do you mean by shells?
Like orbitals around the nucleus.
The orbitals. Okay, do you guys remember about orbitals? Did we learn about those? Thank you. One person remembers, right? Do you guys remember talking about your quantum numbers? N and L and M sub L and M sub S? Two people now. All right, I'm up to almost 10% of the class now. Right? If we just had 3 people nodding, we'd be there, right? Okay. Right, you guys remember about the quantum numbers though? Do you guys remember about the principal quantum numbers and how to figure that out? And what L tells you? Remember, L tells us the shape, whether it's spherical or whether it's a p orbital, right? The S, the P, the D, and the F, and all that kind of stuff, right? And so when I ask you guys about where do electrons live, they are living in those orbitals, and I'm just asking you guys to kind of remember the different blocks and the locations in the periodic table where they are. Okay, I'm not going to ask you guys about quantum numbers in this semester, right? But I would expect you guys to say, well, this is, we've got our valence electrons in the S shell for this atom, right? You guys remember your blocks in the periodic table? The S, the P, the D, and the F blocks, can you guys find those again? That'd be useful, right? If not, take a quick peek at it. And did I post that review for you guys? Or was that for Jen? I forget now. But there are some review videos on YouTube about, what should you remember from Gen Chem, what should you remember from these different classes. So if you guys are kind of, still knocking the rust off from last semester, then it might be a good thing to kind of take a peek at, okay? So, dispersion forces. We're looking at temporary probability of our electrons. Well, what does that mean? Well, you guys are stationary in your seats right now, right? You guys are bristling with energy, sort of, at 8:50 in the morning in a Gen Chem class, right? You guys want to be up and moving around, and I don't know, whatever you guys want to do with your day, right? Maybe go back to sleep. Then my analogy fails, but right? You guys have some energy, and you guys need to get stuff done during the day. Electrons are like that, right? They're always moving around, right? And just like with me, because I'm I tend to be an antsy person, right? I tend to walk around while I'm lecturing, right? If I'm over on this side of the room, then these guys, right, get the full blast of Dr. H's lame analogies and jokes, right? But I have to spread myself out. Otherwise, I'll wear out their laughter over there, right? As you guys can tell, right? I'm already wearing thin, right? Right? I've got to come over to this side of the classroom and work on the jokes over here a little bit, right? Okay, thank you, right? Right? But I've got to be moving around, and just like that, the electrons are moving back and forth, okay? And if I'm an electron, and I'm hanging out over here on this side of the classroom, okay? That means that over here, it's a little bit more negative, right? What about the other side of the room over there? If I'm an electron on a molecule and I'm hanging out over here, then this side of the molecule is negative. What about over there? It's a little bit more positive, right? But how long do I stay over there? Just some of the time, right? And then I start making my way over here. And now this side of the classroom feels negative, right? And what about that over there? Then it feels positive. So that's what we're talking about with the movement of electrons. Sometimes electrons are at one end of the molecule, sometimes they're on the other. And when that happens, it creates partial negatives and partial positives, right? What happens when you put a negative and a positive together? So hang on to that thought, right? You're right, but hang on to that. What happens when you put a negative and a positive close to each other, I should say then? They attract. Got it? So how do all of the intermolecular forces work? We find something negative and we find something positive. Now we have different levels of negative and positive, right? We have partials and we have complete negatives and positives. What happens if I put a full negative and a full positive together? Then we end up making some kind of neutral compound, right? What happens if I put a sodium cation with a chloride anion? What do I end up making? I end up making an ionic compound, a salt, right? A neutral species. Did you guys talk about ionic compounds last semester? Yep. Could you guys name ionic compounds? 2 people again, right? We're still about at the 9% range, right? Do you guys remember the naming, right? We have variant and invariant and the polyatomics. You guys still remember those? I love my polyatomics. They're going to show up on your exams. You guys are going to say, crap, what's a nitrate? I think that's the one with the phosphorus in the middle, right? No, right? You guys remember your polyatomics? They will show up everywhere, I promise. Going back to the statement I made earlier, I wouldn't make you guys memorize something if it wasn't something that's key and important for everything, right? And the polyatomics are one of these things I just harped on. You guys got to know them. Know their names, know their charges. Got it? Good stuff. Okay? So we make these ionic compounds and we talk about that. Now, that's a different type of intermolecular force, and that's sometimes why we have this expanded list, right? Ionic forces are sometimes listed here on your intermolecular forces. And that's just a Coulombic attraction, right? We have a full negative and a full positive. They just come together and they arrange themselves in a specific lattice, right? That kind of thing, right? Now with a dispersion, we're on kind of the opposite end of that. We're on the partial negative and the partial positive. It's me walking back and forth in the classroom here. Sometimes it's negative over here and sometimes it's positive over there. And that separation of charges is going to cause an attraction between molecules. Got it? Now, what if I had you guys all stand up and we all pretend to be electrons? And all of us move to one side of the classroom. Okay? You guys want to do that? Nobody said no. All right. You guys gave you a choice. Everyone get up now. Right? Okay, you guys are with me, right? So pretend that we're all electrons. We all stand up and I make you guys walk over to this side of the classroom. Right? Now we're temporarily over here. But what happens with that negative charge that we build up? It's a bigger negative charge, right? If we're a bigger negative charge because we're all on that side, what about the positive? It's also a bigger positive charge. Well, what happens when you put a negative and a positive together? They attract. And what if I have a bigger negative and positive? What about that attraction? It's stronger, right? It's a bigger attraction. It's a bigger intermolecular force. Is it still a dispersion? Yes, because I'm just temporarily on one side versus the other. Okay? It's just us walking back and forth in the classroom. Got it? Okay, so let's think here for just a second. Methane. CH4. Right? CH4. How many valence electrons does methane have? 4 around the carbon. 8, right? 4 around the carbon and 1 for each of the hydrogens, right? You guys remember how to get your valence electrons? What important, very arbitrary table do we need? Our periodic table, right? Not arbitrary at all. But if you guys can't remember how to get your valence electrons, come see me, guys, or look it up or whatever you do. Right? So if I've got 8 valence electrons, I can move 8 things from one side to the other. Okay? Now let's pretend I have DNA. How many electrons are in DNA? Billions. Okay? Now what happens if I start to move billions of electrons from one side to the other? Is that a bigger charge? Is that going to be a bigger dispersion? What do you think is one of the most important things that DNA uses to attract or repel other molecules? Where it actually does come down to its dispersion. It's massive. It's got a huge dispersion force with it. So the bigger the molecular weight of a compound, right, the higher its dispersion forces. That's what the book says. Does it have anything to do with the actual molecular weight, though? Did I mention anything about weight until the last 30 seconds? No. So does it have anything to do with the weight? No. What does it have to deal with? The amount of electrons, right? That's all it comes down to, right? It just comes down to how many electrons there are. Is iodine heavier than fluorine? Is iodine heavier than fluorine? Yes. Does that matter in terms of its dispersion? No, what matters is its electrons. Got it? Why? Now we could argue about why iodine is heavier and all that kind of stuff, and we could talk about protons, neutrons, yada, 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 right? But you guys get the point? It all comes down to the electrons. And the odd thing about dispersion is it's either the weakest force or it's one of the strongest. When you get to large molecules like polymers and things like that, it's one of the dominant forces in the intermolecular, right? But you kind of have to get to pretty heavy stuff for that. And so that's why in the textbook it says it's the weakest, because we tend to deal with really small atoms, or small molecules in here, okay? But understand that it's, you can get on both sides of the spectrum there with that thing, okay? Good? What do we got next then? So dipole. All right, I'm going to ask you guys the exact same set of questions. What in the world is a dipole charge? We're out treading in the middle of the ocean.
Like the force between 2 polar molecules.
Aha, so the force between 2 polar molecules, okay? So what in the world is a polar molecule? What do we mean by that?
Isn't it like a high partial charge?
Okay, so we've got partial charges again. But what's different about a dipole partial charge than a dispersion partial charge? Maybe. Not necessarily. What's unique about a dipole? How many of you guys have ever played with magnets? All of you guys, right? Okay. Do magnets lose their charge? I mean, if they get hot, right, that kind of stuff, right? But your refrigerator, you guys have a refrigerator magnet you made your parents, like when you were in kindergarten and they still keep it on there. Oh, right? My parents threw it away. Right? You guys give this stuff, as gifts for your kids, right? Do those magnets, lose their charge? Or are they permanently have a positive and a negative end to it? Well, magnets are permanent, right? So what's a dipole? Well, a dipole is a permanent partial charge, right? So as opposed to dispersion, we've got a permanent separation of partial negatives and positives. How does that happen? One important thing that we talked about a lot in Gen Chem 1, do we see a permanent separation of partial charges?
The geometry.
Sort of. You're on the right track. Before we get to the geometry, we need to recognize one thing, though, and then we bring that in. One other very important concept, one of our periodic trends that we talked about.
Electronegativity.
Aha, electronegativity, right? You guys remember that term a little bit? So what is electronegativity then? I saw some nods in the back row there. You want to venture a guess at me? I'm sorry, what is your name?
Chris.
Chris, that's right. sorry, it's gonna take me like 15 weeks to learn their name, and then the semester will be over, but it's good. Chris, what do you remember from electronegativity?
I remember stuff in the top right is more electronegative than stuff in
That's absolutely correct. Do you remember what the most electronegative atom is? What's in the top right of the periodic table?
helium.
Ah, okay, so you're right. You're absolutely correct. So you got me on that one. However, the noble gases are kind of in their own little realm, but you got it there. So if I used to like throw Jolly Ranchers to students who tricked me, but apparently I wasn't allowed to give out candy. But I don't know, it's different here, so. It's like, what is it, like Halloween? Like I'm hiding something in the Jolly Rancher. Anyway, but you're absolutely right. So helium's up there. However, helium is in its own little realm. What is the most electronegative atom, though? Yeah.
Fluorine.
Fluorine, perfect, right? So fluorine's your most electronegative atom, right? What does it mean to be electronegative, though? What is it going to do?
Higher disposition to attract electrons.
Hmm?
Higher disposition to attract electrons.
Aha. So it has a proclivity, a tendency, a disposition, as Laura said there, to attract electrons. How do you attract electrons? Well, how do you attract bees to your garden? Do they just show up? Sometimes, right, if you're unlucky. How do you attract bees to your garden? Or butterflies, sorry, let's make something a little bit pretty, right? Or hummingbirds. Do they just show up for no reason? No, you gotta give them a reason, right?
You have a big garden.
Huh?
You gotta have a big garden.
Gotta have a big garden, right? If I'm trying to attract some butterflies, I better plant some what? Some flowers, right? Something, bird feeders, if I'm trying to attract the birds, right? That kind of stuff, right? Give them a reason to come, is what I'm trying to say, right? So I'm asking you the question, how do you attract electrons to your garden?
It's gonna have a big radius.
Careful.
Positive charge.
I gotta plant some positive charges, right? What is an electron? Something really small that we can barely see, don't really see, sometimes see, right? That has what charge? Negative. How do I attract anything that's negative? Give it something positive. Where's the only positive things in the universe? In the nucleus, the protons, right? That's it. So how do I make something very electronegative? Well, it's got to have a nice, attractive nucleus, right? And who wouldn't want that, right? So the electrons are going to try and get as close as you can to the nucleus. That's all it is. So do you need a big atom or a small atom to be very electronegative? Small, right? Because remember, radius just is a measure of how close you are to the middle. So if you have a really small radius, you're going to be close to where the protons are. That's all. Got it? So remember, we talked about radius and electronegativity and ionization energy and all that kind of stuff. Fluorine is the most electronegative. Oxygen's number 2. Nitrogen's number 3. And then chlorine's number 4. And books are going to argue with me about chlorine and nitrogen, but guess what? I make the rules, right? So the point being is, well, you know, we'll talk a little bit more about that, but for our purpose in here, nitrogen's more electronegative than chlorine is. I think this book agrees with me. I forget if it does. It doesn't matter, right? Well, it does. Actually, it does matter. I should take that back. It always matters. I need to be right. So I'm joking, right? Anyway, so it's always good information, or kind of good to remember the top 4 electronegative atoms. That's going to help you guys predict whether there's going to be dipoles that form and these kind of things, right? So to back up, if we have dipole-dipole interactions, we've got an electronegative atom attached to a less electronegative atom. The more electronegative atom is pulling the electrons towards itself, causing a permanent separation in partial charges. And what happens when you put positives and negatives close to each other? They attract, right? Whether it's a permanent separation or a temporary separation, that attraction is going to happen. Got it? So is there anything really different between a dispersion and a dipole? There's really only one thing, which is what? Whether it's temporary or whether it's permanent. That's it. Got it? It both works the same way. It's negative and positive. Okay? And we could just finish this up real quick and talk about hydrogen bonding there. And hydrogen bonding is just a special case of a dipole-dipole. That's all it is. If you guys can complete the eye exam there, right, it says that hydrogen bonding occurs with fluorine, oxygen, or nitrogen when it's bound to a hydrogen. That is classical hydrogen bonding, right? And the reason why that happens is because there's a big difference in the electronegativity of fluorine, oxygen, and nitrogen as compared to hydrogen. And when you have a big difference in electronegativity, you make partial negatives and partial positives, and things can come together and hydrogen bond and blah, 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 blah. Okay? Hydrogen bonding is one of the most important intermolecular forces on the planet, right? It's what causes ice to float. It's what causes the double helix of DNA to form, right? And those are two pretty darn important things that you guys end up seeing here, right? Those are just two very small, short, trite examples of where it shows up. But anyway, in the next couple of slides, I'm going to go into a little bit more detail. Just going to kind of summarize what we talked about for the last, how long was I yammering? About 40 minutes now? Oof, good, right? It's going to just kind of summarize all that kind of stuff that we talked about there, right? These different ideas of the different intermolecular forces. This right here, right? Understanding that concept that we just talked about is what's extremely important. Being able to recognize intermolecular forces and what that means and what implications does it have and where's your negatives and where's your positives and all these kind of things. Now I tell you that, and you guys are kind of like, yeah, okay, I believe that, right? But the unfortunate truth is, some of these ideas are going to kind of just poof away for Gen Chem 2. They're going to be kind of working behind the scenes, but because of the class and what we're doing here, we kind of have to, shelve some of those ideas for a little bit. But I promise, like I said, for you guys coming on to organic, this is going to be like the first lecture of organic chemistry also. Like these are just core ideas that come back over and over. That's why I spend a lot of time with you guys here on it. Right? Okay. Oh, right. So just one small little distinction here. So remember, the intermolecular forces are between, and if I talk about intramolecular, right, then we're talking about covalent bonds versus ionic bonds and that kind of stuff, right? And we talked about bonding and all that kind of stuff a little bit in Gen Chem 1, but now in Gen Chem 2, we're going to come back and take a look at a little bit more detail about how we calculate certain energetic costs and stuff that comes along with these intramolecular interactions. Okay? Cool. Yeah. So just a little bit of a visualization there, right? There's what we talked about with dispersion forces, moving electrons from one side to the other, right? And just the effects of that and whether we have partial negatives and partial positives. What we didn't talk about is the term of polarizability there, right? Well, I didn't mention that term, I should say. We did talk about it. That's all it is. So when you read in the book and it's talking about polarizability, it's just talking about the electrons moving from one side of the classroom to the other. That's all it is. Okay? It's squishiness, scientific squishiness. Can I shift things from one end of a molecule to the other? Okay? The more I can polarize something, right, just means the more I can spread it out. The more I can create that separation of partial charges. That's all it is. Good. And there's just a little bit more of a visualization of this, but it brings an important idea also, which is why I like this picture. So I asked you guys a couple times about what happens when I put a negative and a positive together. And you guys told me they attract. But what I didn't explicitly talk about is what happens when you put a positive and a positive, or a negative and a negative together. They will what? Repel each other. So if we think about this, right, if we're talking about the electrons moving back and forth, I create a negative over here when I'm standing over here. Now I'll attract a positive, but I'll also do what? I'll repel another negative. So remember, it's always a give and take in chemistry. We create, or I should be careful, what do I want to say here? It's a good interaction when we make something positive and negative come together, right? It's a return of investment. If I'm an electron and I find another proton to hang around with, that's good. But if I'm an electron and there's another electron close to me, that's bad, and we repel each other. So there's good interactions and there's repulsive interactions, right? There's positive interactions in the good definition, right? And there's negative interactions in the bad definition. Does that confuse you guys? I should be careful using positive and negative when we're talking about charges here and that kind of stuff. Do you guys get what I mean with this? Negative and positive good, positive and positive bad. That's all I'm saying, right? So remember, in all of these interactions, this is going to occur, right? Because the principal idea behind every intermolecular interaction is, hey, I've got a buildup of negative, I'm going to attract something positive. That's all it is, okay? Whether it's temporary or permanent or whatever it might be, right? And so they just have a visualization here about how we can see some of these repulsive interactions also. All right. So here's kind of a table for some of these different things that we didn't explicitly talk about. The book talks about ion dipole forces. I'll go ahead and summarize that whole part of the chapter for you. It's something negative attracting something positive, okay? Ionic bonding, we talked about that quite a bit last semester, right? So I'm not really going to talk about that here, right? It's how we know when ions form and how to name them and what are the charges and can we balance them and whether they're soluble and all that kind of stuff that goes along with that, right? The completely Coulombic attractions, right? But what's useful is they kind of give you guys a little bit of a scale of energy there. And what is important to recognize is that ionic bonds are really, really, really strong bonds, okay? Until they're not, but that's a different argument to be had, right? The more, I'll get to you in a second, right? So the idea is this, right? Why do we even see a scale in the in the intermolecular forces? Well, right? It all comes down to how much of a positive or negative we have, okay? That's where the difference comes in. The bigger the positive, that means it's more attractive to negatives. Make sense? That's all it is, okay? What's that?
So is ionic bonding intermolecular and intramolecular?
Yes.
Okay.
Yeah, the difference comes into how do ions arrange themselves in solution and in the solid state,
okay.
Right? There's not if you think about sodium chloride, there's not a discrete sodium and chloride we can pull out. Why do we call it that then? It's because that's the smallest repeating unit in that system, right? That's the smallest neutral system. But if you could zoom in on sodium chloride, you'd see it's just an infinitely repeating lattice of sodium chloride, sodium chloride, sodium chloride. So, right? So you just pull out the smallest unit, and that's what we discuss,
Okay.
right? Because you're right. It's just sodium is just a spherical ion. It's going to attract things from every direction, and that's in fact what happens,
Okay.
right? So it's a little bit different. That's why I say yes to both of those. Right? Cool. All right. So I think that's kind of a good place to stop for today, right? We kind of went through that nice review there. We introduced kind of the ideas and kind of hopefully knocked the rust off of some of the concepts that we remember from Chem 1, right? So we'll continue on with this on Wednesday, and we'll keep working our way through the chapters 11 and 12.
Rusty Jill?
Whoa.